All right. Well, without further ado, I will welcome Dr. François Therrien. He is the curator from the Dinosaur Paleontology at the Royal Tyrrell Museum here in Drumheller, not here in Alberta, but in Drumheller. He is here to present his recent accumulation of findings on what really happened to the dinosaurs. I'm going to stop and I'm going to pass it over to the expert.
Okay, so thank you for having me today. It's a pleasure to be here to talk a little bit about paleontology, and I just presented a shorter version of this presentation to undergrads at the UOC this afternoon, and it's the end of the semester, so I said, well, how fitting to talk about the end of the semester and concluding with a lecture about the end of the age of the dinosaurs. So the extinction of the dinosaurs is a topic that's of great interest to the general public and to scientists in general. So it has received a lot of attention. A lot of people have been studying, as several theories have been proposed to explain the extinction of the dinosaurs. So one theory is that dinosaurs went extinct because of long-term environmental and climatic changes to which they couldn't adapt to, so therefore they went extinct. Other theories suggest that there were major volcanic eruptions that released a lot of gas in the atmosphere, affected climate, and then dinosaurs went extinct in response to those changes. Probably the most popular one is that of a meteor impact that occurred 66 million years ago, created major environmental disturbances to which dinosaurs could not adapt, and that led to their extinction. And then there's some more exotic theories out there that have been proposed over the years. One of them suggested that those pesky little mammals that lived in the shadows of dinosaurs were fond of dinosaur eggs. So they ate a lot of the eggs, and because dinosaurs left fewer and fewer offsprings, they went extinct. Some theories suggest that mammals were physiologically and intellectually superior to dinosaurs. So dinosaurs went extinct because they were dumb, stupid, and maybe forgetful. And my favorite theory is that aliens from outer space came to Earth, abducted all the dinosaurs to bring them back to their home world, put them in zoos, and that's why there were no dinosaurs left on Earth. And then another theory that I found online that's a little perplexing claims that mass extinctions are due to time-traveling ninjas that go back in time and slaughter a bunch of animals, and that's how we get mass extinctions. But regardless of which theory you prefer or you believe, they all try to explain one thing: how the mighty dinosaurs have fallen when the puny little mammals have survived. So today I'll try to present you an overview of what we know about the Cretaceous-Paleogene mass extinction, some of the latest developments on the subject, and conclude my talk with a possible scenario of what actually happened to kill the dinosaurs. But first things first, let's first define what is a mass extinction. A mass extinction is when a large number of species go extinct worldwide, globally. So this means not only on a continent or in a certain area, but all around the world in a geologically short period of time. So here are the key words: a geologically short period of time. This means that animals need not have gone extinct overnight, in a year, 10 years, or a century. So it just means that they went extinct in a on a time frame that's really hard to resolve using the rock record. So for example, if we look at the mass extinction that occurred 12,000 years ago at the end of the Ice Age, resolving the timing of the extinctions to under 500 years is really difficult. If you go back 66 million years ago, resolving the extinction of animals to under 100,000 years is difficult. And then if you go back to the Precambrian, over 1 billion years ago, resolving the timing of extinctions to under 100 million years is really difficult. So here you just have to keep in mind, when we talk of a mass extinction, which just means that it happens on a time scale that's difficult to resolve using the rock record. So let's talk a little bit about the Cretaceous-Paleogene mass extinction itself, or the KPG mass extinction for short. Well, it occurred 66 million years ago at the frontier between the Cretaceous and the Paleogene, and it marks the end of the age of the dinosaurs and the beginning of the age of mammals. So if we look at the past 600 million years, we see that the Cretaceous-Paleogene mass extinction is far from being the only one. In fact, there's 18 mass extinctions that occurred since the beginning of the Cambrian. You can see there's lots of gray bars. Those represent background extinction. Species go extinct all the time and are replaced with others. But in terms of mass extinctions, there are 18 of them that match the definition of mass extinction. And right now, we are living through a 19th mass extinction. So when we talk out of the 18, we usually focus on the big five, the five biggest mass extinctions that happened since the Cambrian. You can see the Cretaceous-Paleogene mass extinction is not the biggest. There's some that were bigger or equal in size, but it is definitely the mass extinction that had the biggest impact on the world we live in today. Without the Cretaceous-Paleogene mass extinction, a world dominated by mammals in which humans could have evolved would probably have never happened. So of course, dinosaurs are the poster children for the Cretaceous-Paleogene mass extinction, but they're far from being the only things that went extinct at the time. There's lots of other organisms that went extinct both on land and in the oceans. So if we look at what happened in the oceans, we see that 90% of the plankton went extinct at the KPG boundary. So given that plankton are responsible for the vast majority of the oxygen we breathe, you can imagine that if 90% of them go extinct, it would have been a big blow to the base of the food webs here on Earth. And then not only it was bad for plankton that lived during the Cretaceous, but even the survivors had a hard time. So here you see images of what the plankton looked like at the end of the Cretaceous. You can see they're very diverse in their shape. Some are very big, some are very small. There's lots of diversity. But if you look at the plankton just after the extinction, you can see they're all very simple in shape and all tiny, very small. So it shows that basically the conditions were very harsh after the mass extinction, that it took a while for the plankton to come back. In fact, it took somewhere between 300,000 and 4 million years for the plankton to come back after the extinction. Surprisingly, marine fish didn't suffer that much. There's only less than 20% of fish that went extinct, but those that went extinct were large predatory fish that were several meters in length. So those all went extinct at the KPG boundary. Then we see among echinoderms, so sand dollars, starfish, sea urchins, we see a little over 1 in 3 species went extinct. More significantly, corals, 60% of corals went extinct. If we look at elasmobranchs, so that's a group of fish that includes sharks, skates, and rays, you can see that over 63% of them went extinct, but it was an even extinction. You can see that skates and rays suffered more than sharks, and durophagus species that crush shells to get their food, suffered more than species that just ate flesh. Then we see that belemnoids and ammonoids also went extinct. Those are squid-like animals that lived in shells. They were everywhere in the oceans around the world during the Cretaceous, but they all went extinct at the KPG boundary. Then we also see the extinction of rudous bivalves and inoceranid clams. Those that work in the oil industry will be familiar with the rudous bivalves. They're clams that are very columnar shaped, and they lived in colonies forming reefs during the Cretaceous. And a big chunk of the oil reserves in the world today, especially in the Middle East, are preserved in rudous reefs like that. And then we have inoceranid clams that are large clams that are up to 2 meters in diameter that also went extinct. And I noticed that when you walk into the building, there's one of those clams on display just near the entrance. So if you haven't seen one, you can go have a look. And then finally, we have the extinction of the mosasaurs and the plesiosaurs. Those are often called marine dinosaurs, but they're not dinosaurs. They're very distantly related to dinosaurs. Mosasaurs are marine lizards. They're very close to Komodo dragons and snakes. And plesiosaurs, like the Loch Ness Monster, they're animals that are more distantly related to the last ancestor of all lizards that are alive today. So if you were to go snorkeling or scuba diving in the ocean at the end of a Cretaceous, that's what you'd be swimming next to. You'd see it would have been a very scary place. But if you went back after the Cretaceous-Paleogene mass extinction, you'd see that most of these animals would be gone and the ocean would look very pristine and clear, what we call a Strangelove ocean after Dr. Strangelove movie, where he sees purity in death, basically, when there's nothing left alive, he sees that pure. Well, that's what happened, that the oceans would have appeared pure because everything was dead. So now what happened on land? Well, we know actually very little about the extinction of animals on land because the only good record we have of the end of the Cretaceous is here in North America between Alberta and South Dakota. That's the best pocket we have of fossils for the very end of the Cretaceous. We know nothing of what went on elsewhere in the world. So we'll go over what went extinct and how they suffered, but keep in mind that this is true for this part of North America. It may not be true for what happened elsewhere in the world. So for land animals, we see animals that suffered tremendously through the KPG boundary, and then some animals that went through relatively unscathed. And among those that suffered very little extinction, we see the Champsosaurs. Those are crocodile-like reptiles, turtles of freshwater and freshwater fish, crocodiles, and salamanders. These animals have very low extinction levels, so didn't suffer very much across the boundary. Then we see animals that suffered a lot. Frogs suffered high levels of extinctions, and even mammals. And that may be a surprise because we often say that mammals are the big winners of the Cretaceous-Paleogene mass extinction. But in reality, you see that 3 and 4 mammals went extinct. And depending on what type of mammals you were, if you were a marsupial like opossums, you were almost wiped out. But if you were a placental like us, then 1 in 2 species went extinct. Then we see again, lizards and snakes suffered a lot, and also birds. We have entire lineages of birds with teeth that went extinct at the KPG boundary. But the only survivors were a group of modern birds that had beaks, that didn't spend much time in the trees. They spent more time on the ground. They probably ate seeds. And the only lineages that survived were the lineage leading to tinamous and ostriches, the lineage leading to ducks, geese, and chickens, and the lineage leading to all other birds. So essentially, birds in general suffered a lot also across the mass extinction. And then finally, we have groups that went totally extinct at the boundary. We include the flying reptiles, the pterosaurs, and of course, all non-bird dinosaurs went extinct. So why did dinosaurs go extinct? Well, dinosaurs ruled the earth for over 160 million years. So for them to go extinct, it would have, well, it attracted a lot of attention. So there were lots of teams that tried to come up with different explanations. So we can group their theories in 2 grand schools of thoughts. The first one suggests that dinosaurs went extinct suddenly because they were so successful that the only way they could have all gone extinct is if a sudden catastrophic event occurred to wipe them out. Then another school of thoughts thinks that they can see in the fossil record evidence that dinosaurs were already on their decline. They were gradually going extinct millions of years before the boundary, and that they just went extinct normally without any special cause. So the debate between these 2 teams has raged on for since the 80s, so almost 40 years now. And about 10 years ago in 2014, there's a paper that came out that was published that compiled all the data and made a very strong case for a sudden extinction in dinosaurs. So they looked at diversity of dinosaurs for the last 80 million years of the age of the dinosaurs, for the entire Cretaceous period. And if we just look at the 2 curves here, represent the diversity in the world, diversity of dinosaurs in North America, you can see that the diversity numbers don't change much through time. It stays pretty flat. So it's evidence that there was no long-term decline in dinosaur diversity over the last 80 million years of the age of the dinosaurs. But what about the possibility there could have been a gradual decline in the last couple million years before the extinction? Well, the team looked at the fossil record from North Dakota, where every fossil that was collected has been the exact stratigraphic position in the rocks has been recorded and calibrated in time relative to the Cretaceous-Paleogene boundary. So each dot on this graph represents a fossil that was found in the rock record. So they see that when you look at the rock record, that you have a high diversity of dinosaurs up to about 115,000 years before the boundary. So their dinosaurs are still going strong at least until 115,000 years before the KPG boundary. Then you still look at 50,000 years before the boundary, there's still lots of dinosaurs around. There's some that have gone extinct, or at least for which we don't find fossils, but those are usually rarer species that we rarely find in the formation anyway. And others are from species like, for example, Pterosaurus and Triceratops. Those are two-horned dinosaurs. It says that they're not there, but we still have fossils of horned dinosaurs. It's just that they're not complete enough to say if they're Pterosaurus or Triceratops. So it's quite likely that these two species were still there 50,000 years before the extinction event. And then you can see that in the last 50,000 years, the fossil record becomes extremely poor. And just a statistical fact, if you try to find fossils really close to a random level, odds are that you're not going to find anything right below the line you're looking for. So it's probably just a preservational artifact that we don't find any fossils there, or just very few. So if we look at that, well, the fact that dinosaurs were going strong until 115,000 years before the boundary, and possibly even closer to the boundary, possibly even up to the boundary itself, suggests that it was a sudden extinction event. And if you look at the fossils of other animals, whether they're fish, amphibians, turtles, lizards, crocodiles, you can see there's lots of them below the boundary, and they make it all the way to the boundary. But above the boundary, you suddenly have a big wipeout. There's very few animals surviving. There's a low diversity fauna that's just composed of survivors. And what's interesting about the KPG mass extinction is that it was selected. This means that depending on who you were and what you were doing, that affected your chances of surviving or going extinct. For example, if you were an aquatic animal, you were cold-blooded, you were small, and you didn't lay eggs, odds are your chances of surviving were way higher than if you were a terrestrial animal, you were warm-blooded, and you were large. So depending on what you were doing, that affected your chances of survival. And in fact, as a rule of thumb, if you were small, you weighed less than 20 kilos, so that's about 45 pounds, and you were a generalist, meaning you could eat a little bit of everything, then chances are that you would survive. But in contrast, if you were large, meaning you weighed 45 pounds, which is the vast majority of us here, we are mostly way above 45 pounds, and you were a specialist, meaning you were a strict herbivore or strict carnivore, then you were essentially doomed for extinction. What could be the cause of the mass extinction? Well, when we're trying to build a theory or a scenario to explain the extinction event, you need to take into consideration two factors. First, your theory needs to be able to explain the extinction of dinosaurs and of other organisms. Dinosaurs are not the only ones that went extinct. So that's why I always laugh when I hear a new theory. Oh, dinosaurs went extinct because mosquitoes were spreading diseases and they all died. Well, okay, well, how do you explain the extinction of turtles? How do you explain the extinction of mosasaurs in the oceans? Did your mosquitoes wear scuba gear to go and infect the mosasaurs in the oceans? So that's why your theory doesn't stand. It needs to explain how everything went extinct. And also, it needs to explain how something survived, how your scenario can explain the selective nature of the animals, how not everything was affected equally. So now we'll have a look at what events occurred at the end of the Cretaceous that could have had a role to play in the mass extinction. So first, we know that sea levels were fluctuating a lot. So here, if you look at the blue line here, it represents sea level. The farther to the right it is, the higher the sea level is, and the farther to the left the line goes, the lower the sea level was. So you can see that as you get close to the KPG boundary here in red, you can see that the line declines, goes to the left fairly steadily. So it means that sea levels were dropping in the last few million years before the Cretaceous. If you look at what the world looked like at the end of the Cretaceous, you can see here we're looking at the world 10 million years before the extinction event, you can see sea levels are extremely high. Most of the continents are covered by shallow seas because the water levels are high. But then if we fast forward to the Cretaceous-Paleogene mass extinction, we can see that most of these inland seas have retreated. The water has gone back into the oceanic basins. And here in North America, that's what we call the Bear Paw Sea regression. So there was a big inland sea, the Bear Paw Sea, that divided North America in two halves. And then that was 10 million years before the extinction. Fast forward to the day of the extinction, you can see that big inland sea is retreating to the north and south, such that now the continent is mostly continuous or connected from east to west. Number two, we know that there were periods of climate fluctuations or climate change during the Cretaceous. And you can see that from the late Triassic, the origin of the dinosaurs, all the way through the Jurassic and into the early Cretaceous, the world was a very warm place. The climate was very warm. There was not much fluctuation. But when you go into the late Cretaceous, then the climate starts going on a roller coaster with lots of fluctuations between a greenhouse world and what we call an ice house world, the world that would have been cold enough to have ice at the poles. So here, if we look at the last 8 million years of the Cretaceous, we can see there's lots of fluctuations in temperatures. You can see we have big sharp spikes of temperatures followed by big rapid drop in temperature. So the climate is going on a roller coaster. And if you look at about 20,000 to 100,000 years before the extinction event, you can see that temperatures are dropping super fast, about 6 degrees Celsius of mean annual temperature. 6 degrees Celsius is the difference between the world we live in today and the temperatures 20,000 years ago during the last glacial maximum. So it's a big difference in temperature that occurred over a very short time span. So there's no doubt that this drop in temperature would have put a lot of stress on ecosystems, both on land and in the oceans, and that probably would have created a lot of instability in those ecosystems. We also know there was volcanism taking place at the end of the Cretaceous in the subcontinent of India. There were big fissures that opened in the crust, and lava flows, basalt flows just started pouring out of the earth, and just basically those lava flows just started piling on top of one another, forming a big plateau that we call the Deccan Traps. That's up to 2 kilometers in thickness. You can see here all those black lines there, they're all layers of lava that are just piled on top of one another. And those weren't just small eruptions. The lava flows covered over 500,000 square kilometers of the Indian subcontinent. Just to give you an idea, 500,000 square kilometers is just slightly smaller than the province of Alberta. So imagine burying the province of Alberta under 2 kilometers of lava flows. It just gives you an idea of the sheer size, the sheer volume of volcanic eruptions that took place. So of course, volcanic eruptions release a lot of dust in the atmosphere, a lot of gases that could have affected climate, polluted the air. So it could definitely have had an impact on the mass extinction. But scientists don't agree on when those eruptions happen. We know they happen really close to the KPG boundary. But one team has looked at the lava flows, obtained radiometric ages, and they found here those are the volume of lava from different eruptions. We can see that there's some eruptions before the Cretaceous-Paleogene, I should say. To the right is in the past, and to the left is towards the present. I don't know why they inverted the scale bar. Usually we go to the right, but they decided to make their graph to the left. So you see before the KPG boundary, there's very few lava flows, but after, that's when the vast majority of the lava flows, the biggest volumes of lava flows were put in place. So this means that probably volcanic eruptions did not have a big impact on the extinction itself, because most of the volcanic activity happened after the extinction. However, it could have had an impact on the recovery. It could have delayed the recovery from the mass extinction for probably millions of years. But then that's one team, they believe that. And the second team, using exactly the same rocks, using the methods to determine the age of the rocks, found that volcanic eruptions occurred both before and after the extinction. So now We don't know what's going on. If the volcanic eruptions started were significant before the boundary, then they could have had an impact on the mass extinction. So what's the reality? We don't know. We'll need more research to be conducted to actually determine more precisely when those volcanic eruptions, the timing of those volcanic eruptions. And then finally, we know that there was a meteorite impact that occurred at the end of the Cretaceous. How do we know that? That's because we find an iridium anomaly at over 100 sites around the world. Iridium is a type of metal that's very rare at the surface of the Earth, but is very abundant inside the Earth and in meteorites. So how do we know that the iridium comes from a meteorite and not from volcanic eruptions? That's because we find other lines of evidence suggesting there was an impact at the time. One of them is called shocked quartz. So quartz is a very hard mineral. Picture this is a grain of sand, and the mineral is so strong that usually it doesn't get deformed. But you can see that at that layer where we find the iridium, we see that the sand, the grains of quartz are fractured, what's called shocked quartz. You can see there's lines of fractures within the grains that are really, really tight. And that type of breakage only happens when quartz is subjected to to conditions of high pressure and high temperature, just like what happens at an impact site. Then we also find tektites. Those are tiny little beads of molten rock that were ejected out of the crater and cooled really quickly in the atmosphere and just started raining back down on the surface of the Earth because it had been ejected out of the crater. So because we find the iridium associated with shocked quartz and tektites, that's how we know that there was an impact at the KPG boundary. But where was the crater? There were lots of craters around the Earth, but none of them dated back to the Cretaceous-Paleogene boundary. That was a mystery for decades. It wasn't a deal breaker that we didn't have a crater, because it could have been buried under lots of sediment, could have been eroded away, and if the impact had occurred in the ocean, maybe it was buried deep, or maybe it had been even at a plate boundary due to plate tectonics. The crust had subducted back into the mantle and had been recycled, so we would never actually find the crater. So just the fact we didn't have a crater wasn't a deal breaker. But then in the 80s, Mexican oil companies started looking for oil in the Gulf of Mexico, and they came across a circular anomaly under the Gulf of Mexico. So they kept it secret at first because they didn't want other companies to know where they were looking for oil. But eventually the word came to the ear of a young PhD student who's now a professor at the U of C, Dr. Alan Hildebrand, and he was studying KPG boundary sites in Haiti. And with the data from the oil company, he studied the site and discovered that, yes, the crater was right at the KPG boundary, and it was a crater of meteoritic origin, not a volcanic origin. So the crater is situated halfway under the Gulf of Mexico, and half of it is under the Yucatan Peninsula there. If you were to go to that area, oh, and I forgot to say, because the epicenter, the center of the crater, is close to the small town of Chicxulub in the Yucatan, that's why the crater was given the name the Chicxulub crater. Now, if you look at Chicxulub today from outer space, you don't see a big hole in the ground. You can see the nice Yucatan Peninsula, very green, and the blue waters of the Gulf of Mexico, but the crater is there. It's just buried underground. If you go to the town of Chicxulub there, you can see it's a quaint little town on the Mayan Riviera. Obviously, they're selling some houses over there that they want you to know about, but you can see it's very flat. There's no hole there. If you go to the town, you'll see there's basically right at the exact epicenter of the crater, there's a little monument there with dinosaurs and a bone-shaped sculpture that says in Spanish that this is the epicenter for the Chicxulub crater. And then if you search really hard in a town, you'll find the only remain of former research station where they actually drilled the core all the way down to the center of the crater in the 80s. Now it looks like a washed out board that you have a hard time reading, but at least you can see the Coca-Cola sign very well. So yeah, so there's nothing to see at the Chicxulub site itself because everything's buried. I think it's over a kilometer under the surface. So the only way to see the crater is to use different methods. either seismics or gravity anomalies to try to detect it. So here you can see, based on anomaly, magnetic, or I think it's gravity anomalies, you can see there's a round structure on the ground, and you can use software to produce a 3D model of that crater. So that's how we know that the crater is still 180 kilometers wide, 20 kilometers deep, and formed in evaporites and the crust. And based on the shape of the crater, we can infer, well, there's ways to calculate, there's a relationship between the speed of your impactor, its size, and the size of the crater. So they were able to back calculate that the meteor would have been 10 kilometers wide and would have been flying from the northeast and impacted with the crust at an angle of 45 to 60 degrees relative to a horizontal. So it was actually an angle that it came at. So if you look at what the world looked like at the end of the Cretaceous, we see the crater and the meteors coming from the northeast and then splashes down into the Gulf of Mexico. It wouldn't have been a dead-on collision. There's very few dead-on collisions in the solar system. It represents less of 7% of the impact are from dead-on collisions. Rather, it was an angled collision. That's been calculated that about 75% of impacts in the solar system were collisions that were 60 degrees or less. And we said that, yeah, the impact for the Chicxulub crater was between 45 and 60 degrees. So it would have been normal for a meteorite. So those dimensions, a 10-kilometer meteorite, 180-kilometer wide hole, it's kind of hard to understand what it truly means. So I've put that in context so that we can actually better understand how big the impactor or the meteorite was. So we said that the bolide, the Chicxulub meteorite, was 10 kilometers wide. How big is that? Well, that's the size of the town of the city of Red Deer. So imagine a chunk of rock the size of Red Deer coming down and colliding with the earth. If you're not familiar with Red Deer, you're familiar with Calgary. Well, 10 kilometers, that's the distance from the Saddle Dome to the airport. So it gives you an idea of the distance, how big that rock was. If you're familiar with Vancouver Island, the Victoria area, 10 kilometers is essentially from Victoria all the way to, it's called Elk Lake on the way to the airport. The airport is somewhere around there. So 10 kilometers is that big. Or if you want to know how high 10 kilometers is, if we were to roll a 10-kilometer wide meteor at sea level, the other end would be higher than the Everest and would reach the cruising speed of commercial jet planes today. So it gives you an idea of how tall that chunk of rock was. And now we said the Chicxulub crater was 180 kilometers wide. So how big is that? Well, if you put that over Alberta, the crater would go from Calgary and 2/3 of the way to Edmonton, to a small town of Ponoka, about 50 kilometers north of Red Deer. So it's and that hole would have been 20 kilometers deep. So this means twice the altitude of flying commercial planes. So odds are, if you were standing on the rim, you wouldn't even see the bottom of it because it would be so dark, you wouldn't see what's at the bottom of that crater. And again, if you're familiar with Vancouver Island, 180 kilometers is basically, if you were standing on the periphery of the crater, that crater would go from Victoria to Vancouver, come back to Ucluelet, and back there. So 180 kilometers, it's about halfway between Victoria and, it's the distance of Victoria to halfway between Tofino and Ucluelet. If you've driven it, it's 4.5 hours, I think. So it's a long distance. So what's really interesting, if we look closely at the ring, the crater, we see that it has a ring inside of it. And that's really unusual. We can see it in there too. Craters will often think of big circular holes in the ground, but this one has a ring in it. So it's really unusual. We don't really know how these form, but we know that they do happen elsewhere in the solar system. You have peak rings on the moon, like Schrödinger crater here near the South Pole, where some of the missions are going now. You can see it has an inner ring. You can see craters on Venus that have inner rings. On Mercury, right here. On Callisto, one of the ice moons of Jupiter, you can see it has a series of concentric rings around that crater side there. And we also find them on Earth exposed at the surface. That's a crater in Chad. You can see here that's the crater rim. and inside there's the ring. And here's a digital model, elevation model of the ring. You can see the walls there about 100 meters high. 100 meters, if you've been to Dry Island, Buffalo Jump, and you're standing at river level, 100 meters is prairie level over there. So they're very, very tall structures, both the crater rim and the inner ring there. In Quebec, here in Canada, we have Clearwater lakes that actually one of them has a clear ring inside, and probably one of the most impact crater is the Manicouagan crater also in Quebec. Lots of people see that circular lake and think that that's the rim of the crater, but in fact, it's actually just a ring. It's a trough just before one ring. There's another ring inside, and the outer rim of the crater is very, very far away. It's 150 kilometers in diameter. So we have peak rings on Earth, but a lot of them are eroded. So here we're lucky that for the Chicxulub crater, we have perfectly preserved rings. They're just buried 1 kilometer below the surface. So there's a team that went on a boat and they drilled all the way down through the Gulf of Mexico and into the rocks to hit the rings to determine how those things form. So here, what they were able to determine, they realized that when the impact took place, in the first minute of the impact, not only the meteorite totally vaporized, but it also vaporized a hole in the crust that was 20 kilometers deep and probably close to 100 kilometers in diameter. Now, all that rock just vaporized and got ejected up in the air within a minute. And then in the 2 minutes that followed from T+1 to T+3, the rock of the crust that was used to be buried 20 kilometers deep now no longer has mass keeping it down. So it just explodes, basically just projects up in the atmosphere up to 15 kilometers in altitude. So that's a time and a half higher than jet planes, and just basically stays up there for 2 minutes. And then in the following 7 minutes, that big pillar of rock just comes back down and flows back into place and forms those a circular ridge that forms actually the inner ring of the crust. So that's how violent that impact was. And if you were to go to the side there in the early Paleogene, you would see that what it would have looked like, probably like a little piece of paradise here on Earth, very beautiful. But before we get to that place, we had to go through hell to get there. So here a team decided to create a computer model of what would have been the aftermath, the first 10 minutes after the impact. So here they build a model. You can see that they produced just a half model, but it would be symmetrical on both sides. So here, this is the bullseye, the meteor that's about to collide with the Gulf of Mexico. There's sediment underneath, and then there's a crust. And notice the scale. That's 40 kilometers in altitude. So we're really looking at something on a very large scale. So I want you to first, it's going to be a video. It's going to go fast. So I'll just give you a few tidbits what to look for. First, just focus on what's going on at this left end of the diagram. You'll see that in the first 60 seconds, the first minute, you'll see that the big crater, the impact will happen. A big crater 20 kilometers deep will just instantly form itself because the rock just gets vaporized and ejected up in the atmosphere. And that hole, will be 20 kilometers deep, but closer to 100 kilometers wide. In the following 2 minutes, from 1 minute to 3 minutes, you'll see that the crust is just projecting up in the atmosphere, 15 kilometers in altitude. And then in the fall, from 3 minutes to 10 minutes, that pillar of rock will just come back down. So let's have a quick look. I think we can use that. You guys are ready? So here, this is what happens. Craters forming, ejecting debris. You can see here, the mountain of rock is just projecting up 15 kilometers high, and then everything comes and back, settle down. It wiggles a bit for the following 7 minutes to stabilize, and it's at that time that the ring would have formed. So that's how the crater was formed. Now we'll have a look. Whoops. Yeah, oh, it just repeats itself. Okay, so there. Now let's go to the next one. Now let's pay attention to what's going on the right side of the screen, because the impact happened in the ocean, in the Gulf of Mexico. So now we'll see what kind of waves, the tsunami that was produced by that impact. So you'll see that in the first 2.5 minutes, basically there's a wall of debris of ejecta that projects water all the way up to 40 kilometers in altitude. 40 kilometers high, that's the stratosphere. That's where the ozone layer is. So it just gives you an idea of how high all that material is ejected. Then after 2.5 minutes, you'll see that things are settling down, water falls back down, and then you have an initial wave that's 4.5 kilometers high that starts traveling through the Gulf of Mexico towards the coast. And then from 2.5 minutes and that forms about 70 kilometers away from the impact site, because it's total chaos closer to that. Then from 2.5 minutes to 10 minutes, you'll see that the big wave collapses down. It's going to look very small there, but it's still a wave that's 1.5 kilometers high, that's traveling, that forms about 220 kilometers away, and that travels at close to 200 meters per second through the Gulf of Mexico towards the shore. So let's have a look at that. Now, ignore the big hole there. Just pay attention to what's happening in the water, to the water. So you can see it's ejected at 40 kilometers high, things starting down. That's your 4.5 kilometer high wave, tsunami wave. Water falls back from orbit. And then you can see now it's settling down into a 1.5 kilometer high wave that's just traveling across the Gulf of Mexico towards the shoreline. So it's basically everything is on gigantic scale there. These scientists have followed the models and see how the tsunami propagated across the world or the world's oceans. So you can see that that's wave height. The redder it is, the higher the waves are. So obviously, the tallest waves are in the Gulf of Mexico, where the impact took place, where they reached up to 1.5 kilometers in altitude. But when they go out into the Atlantic and into the Southeast Pacific, they come back down to about, I can't remember, I think it's around 10 meters in elevation. So very big waves. And you can see the rest of the oceans, the waves die down really fast and come to be about 50 meters, between 50 meters and 10 meters in elevation. If you look at the speed of those waves, obviously close to the impact site, the waves are super fast. In the Gulf of Mexico, they reach 200 meters per second. And as you get out into the oceans, you can see it slows down to somewhere around 20 to 10 meters a second. And along the coastlines, actually, that's where it reaches 20 meters per second or higher. And that's enough to erode all the sediment that's there. So imagine all those pristine beaches, the soft sediment, all that is just scraped away bare, and you're back to bedrock to form the coastlines. So here's a little animation that shows how the tsunami spread away from the Gulf of Mexico. You'll see that an hour after impact, you see that in the first hour, the waves just splash back and forth through the Gulf of Mexico. Red meaning they become really high, blue means they become really small, the water level drops. So you can see that in the first hour, just basically the inside of the Gulf of Mexico just gets beaten by the wave ceaselessly. And then after an hour, the tsunami enters the North Atlantic Ocean. After 4 hours, it enters the South Pacific by going between the, the Central American Seaway. 7 hours later, you'll see that the Gulf of Mexico has essentially emptied itself. You'll see water levels are much lower than they were before. 14 hours later, you'll see the water rushes back into the Gulf of Mexico. And then you can see another series of waves coming to crash against North America. 28 hours later, you see again the Gulf of Mexico empties itself once again. And 36 hours later, the water comes back, and then another series of waves come crashing there. So it's like in a big bucket when you start shaking it like that and see the water splashing back and forth. That's what's happening there. So now we'll look at the first 2 days after the impact. You can see, boom, the impact beating the North America, spreading into the Atlantic, spreading to the Pacific. You see blue here. This means the Gulf of Mexico is empty. Then the water comes back in and you see big waves that come back to crash against North America. Then you'll see, oh, it becomes gray, becomes blue again. So the water gushes out of the Gulf of Mexico again. And now you can see the wave close to 36 hours later, the water comes back in, and then there's another wave front that comes and crashes against North America. And then after 2 days, the oceans return to normal, the tsunami is gone, but there's damage everywhere that's done. I have an animation like that for around the world. So if you're interested, just come see me after the presentation and I'll play it for you. See here, now the tsunami hits North America. What kind of damage does it do? Well, we see that at T0, which is there, we'll see that the crater forms, boom. And then after 2.5 hours, you can see that's when we have the 4.5 kilometer high wave spreading away from the crater site. 10 minutes later, sorry, 10 hours later. Oh no, sorry, 10 minutes later, yes. So you have the wave that's now 1.5 kilometer in elevation that's spreading towards the coastline. And then after 2 hours and 15 minutes, that's when the waves hit the platform or the shelf of North America. And what happens when waves come and hit the shallows? They go up in elevation and they start spreading their energy and basically creating lots of damage. In fact, we find tsunami deposits all along the coast there, lots of debris. Some are just big chunks of carbonate platforms that have been jumbled together and even graded by currents. And along the northern Gulf of Mexico, the coastline there, have lots of sandstone that preserved big sedimentary structures, indicating that big waves came crushing against the coast. Unfortunately, those big structures are not visible at the surface, but there's a recent study of researchers in Louisiana that actually used seismic methods and actually looked at a layer of sediment that's 1.5 kilometers below the surface that represents the bottom of the ocean or the bottom of the continental shelf at the end of the Cretaceous. And on it, you can see all that wrinkled texture. Those are big, giant dunes of sand that are preserved at the surface of that layer that actually were formed by the tsunami. So you can see here, those structures are asymmetrical. This means those are big sand waves that were just pushed by the tsunami towards the coastline. And in the deeper part of the shelf, you can see that those are big dunes. They're 16 meters high. That's gigantic. And they're about 600 meters apart from crest to crest. When you get closer to the coast, then the ripples become smaller. 3 to 6 meters is still pretty big, but they're smaller than there. And then they're getting closer to one another, about 365 meters apart. So unfortunately, we have very little evidence of what happened on the coast itself. We have the sediment underwater close to the beaches, but we don't have material on the coastline itself, probably because it was just destroyed by what happened. There's one site in Baja California that preserves big trees that have a diameter of 1.5 meters and are 3.5 meter longs that have been washed out to sea, probably by landslides and maybe the tsunami. And those trees are totally burnt, charred at temperatures over 1,000 degrees Celsius. It means there was probably a fireball that happened as well and just devastated all the forests. And then some of the trees fell into the oceans that are preserved in Baja California. But here again, we see the only record that we have of the impact on land is from debris that was ejected out of the crater and fell down on land up to 4,000 kilometers away here in central Alberta. We have what's called the boundary claystone. You can see it's a little layer of mud that's salmon colored, a little pinkish, and that's very fine grained. And that's the debris that represents the debris that were ejected out of the crater. And we find that boundary claystones at many sites around North America, but by far the best studied one are the boundary claystones here in Alberta. My colleagues, who's now retired, Dennis Brayman, the late Art Sweet from the GSC, and myself have contributed, well, in different parts on the study of the KPG boundary. If you travel about an hour north of Drumheller to the Knudsen's farm, where some of you may have been on a field trip. You can see here, this is a rock formation that represents the last 900,000 years of the Cretaceous. The KPG boundary is preserved right at the base of that coal layer right there. You can see it right here. So by studying the plants, the remains of the plants, mainly the pollen and the chemistry, that's what I studied, the chemistry of the rocks below the boundary, through the boundary, and above the boundary, we can actually reconstruct the sequence of events that occurred after the impact. So what do the rocks tell us? From 3 meters below the boundary to just below the boundary, so probably the last 20,000 years of the Cretaceous. Here in Alberta, we had a moderate to low diversity forest that was dominated by flowering plants and ferns. So that's probably what the landscape looked like. It was a little bit marshy, wet, but you still had very nice forests and dinosaurs were living happily. Then the day of the impact happened, debris starts falling down from the skies, and that's what we call the ejecta layer. And in that layer, we find a lot of tektites. Those are those little beads of molten rock that are raining down from 4,000 kilometers away. And that's mixed in with the pollen from the trees that were growing at the time. So that's probably what the landscape looked like when that layer formed. There's probably lots of wildfires, the trees are dying, and then the ground is covered with ash and the tektites, and mixed in with that stuff on the ground is all the pollen from those trees. Then higher up in the boundary claystone, we have what's called the fireball and the vaporized material layer. So that's the fallout, what was up in the atmosphere and started raining down in the days to years after the impact. So we see that in the upper part of the boundary claystone, there's no trace of the Cretaceous plants. They've all gone extinct. The only things that are still growing are ferns, and there's nothing else. Those are the only plants growing on the landscape at that time. We also see, based on the carbon signature, that the terrestrial ecosystems have totally collapsed. The trees are gone, the forests out of whack. So there's this terrestrial carbon cycle is totally done. Interestingly, we see no evidence of extended darkness or cold following the impact. You may have heard lots of stories about a nuclear winter after the impact, that, oh, it was dark, it was cold, there was snow on the ground, it was horrible. Well, all those explanations, they're all based on computer models. The scientists have never gone to the fossil record to see if that truly happened. And based on what's happening here in Alberta, we can say that no, there was no nuclear winter after the impact. Sure, there was less light, lower luminosity, and cooler temperatures, probably because there's lots of dust in the atmosphere covering the entire planet, but we're still not getting freezing temperatures. And what we have to keep in mind is that south central Alberta, back in the Cretaceous, was at the same latitude as Fort McMurray. So if there's no snow in the winter in Fort McMurray, there's probably not no snow anywhere else on Earth. So basically, yeah, so there's no nuclear winter after the impact, no snow, and that would have lasted for about 10 years based on the number of laminations we see there. So this is what the world would have looked like 1 year after the impact. You can see all the trees are dead, the ground is bare, but then you see you have little shoots of ferns that are springing out, and that's because ferns are colonizers. They're the first plants to come back after a catastrophe. So you can see if you're a herbivore and you have to wait a year to eat something, there's probably not much for you to eat, especially if you don't like ferns, you're probably going to be starving to death. And this is what the landscape would have looked like 10 years after the impact. You can see it's lush, there's lots of greens on the surface, the trees are still dead, but the ground is covered with greeneries. But again, it's only ferns. Ferns will colonize for 10 years before other species can move in. So again, if you're a herbivore, you probably starve to death long before you get to that point. And then all the predators that were feeding on herbivores are probably gone as well. So then the first 10 centimeters after the boundary, we see that we have deposition of coal. Coal is organic matter. So this means that there were probably lots of plants around that basically shed debris into a little pond, and that could turn into coal. So this means that plants are back. And if you look at what the pollen is saying, you see that we're back to more normal conditions of light and temperature, typical of what we had before the impact. But the ferns that were there before are gone, but we have new ferns that are moving in. There's not much else. There's a few flowering plants that are coming back, but the evergreens are not back, so we still don't have a forest. We have lots of ferns, a few bushes of flowering plants, but nothing else. And then the terrestrial carbon cycle is still gone, not coming back. So this is what the landscape probably looked like. You see lots of ferns covering the ground, and then the only little bushes are flowering plants, but we don't have big forests yet. And then starting 10 centimeters after the boundary and up, that's where we have a full recovery of the forest. Now we're back to canopied swamp forest dominated by evergreens and flowering plants. And that probably occurred in as little as 5,000 years. Now that's very, very fast. You think that basically forests are back after total devastation. They're fully back to pre-impact conditions within 5,000 years. In the oceans, it took between 300,000 years and 4 million years for conditions to come back. So 5,000 years is relatively fast, and that's what we have after 5,000 years. We have beautiful forests with tall evergreens and canopy of flowering plants. What happened to animals? Well, it took longer to animals to come back. If we look at mammals, those were the big winners of the extinction. Can see that it took them between 400,000 years and 1 million years to come back to diversity levels that we had before the impact. So it took them a lot of time compared to the trees. It took them only 5,000 years. The earliest Paleocene mammals were all small, raccoon or smaller, and they were generalists, meaning that they ate a little bit of everything. They didn't have strict herbivores or strict carnivores. They just ate whatever was available. They weren't picky. And then large mammals, we're talking about a small cow-sized animal. Those didn't evolve for 5 million years. So it took a long time for mammals to really reclaim the earth after the mass extinction. So we're at the end. What is the cause of the mass extinction? Is it climate? Is it volcanism? Or is it impact? Okay, show of hand. Who thinks it's volcanic eruptions? Nobody. Climate change? Nobody. The impact. Okay, most of you think it's the impact. The impact is definitely the most popular story scenario, but there's a study that was published in 2008 that unfortunately hasn't received much attention, but they make a very strong case to say that it's not one cause, it's a combination of all those things that led to a mass extinction. And here's their reasoning. If they've looked at events that occurred over Earth's history, and they classify them into two categories. There's press factors and there are pulse factors. Press factors are events that alter a community by putting long-term pressure on those ecosystems. So it's not something very sudden or very intense, but it's sustained over a long period of time. And that includes climate change, sea level change, and volcanism. Pulse events are sudden and catastrophic events that cause a lot of mortality, that cause a lot of animals to go extinct suddenly. And that includes meteorite impact and anoxic conditions in the oceans. So what they did is they classified those events for the last 250 million years from present to essentially the Permo-Triassic boundary, and looked at when these events occurred versus when mass extinctions occurred. And they discovered that mass extinctions only occurred when the two factors coincided, happened together. So you needed, if an event, a press event that was present to destabilize the ecosystems, happened at the same time as a catastrophic event to push the ecosystems over the edge, that's when you had a mass extinction. If you had only one or the other of those factors, there was no mass extinction. Sure, there may have been some local extinctions, but there was no global mass extinction. So in the case of the Cretaceous-Paleogene boundary, our press factor is climate change. We saw that in the last 20,000 to 100,000 years of the Cretaceous, there's a sudden drop, very rapid drop in temperature of 6 degrees Celsius that probably destabilized ecosystems. And then at the worst time possible, when the temperatures get to their coldest, That's when we have the meteorite impact that just pushed the ecosystems over the edge and led to a mass extinction. If any of those factors had occurred on their own, dinosaurs probably had not gone extinct. In fact, I've done a study on using the fossil record of Alberta, where we see before the boundary, there's lots of periods of climate change. We saw that roller coaster ride, but dinosaurs did not go extinct. And diversity did not even flinch, didn't even change during those periods of climate change. So I think dinosaurs are very resilient. They're capable of dealing with climate change. Probably it's possible that their numbers went down, but the species did not go extinct. They made it through, and then when temperatures warmed up again, they were back and running and everything was great. And then for impacts, we have lots of impacts during Earth's history. Some impacts are just as big as the Chicxulub impact, but we can't tie them to any mass extinction event. We know the timing of the impact, but there's no mass extinction that occurred anywhere on Earth. So it shows that, yeah, sure, an impact like that will probably kill lots of animals in the area of the impact, maybe on a continent, but may not lead to a global mass extinction. So that's a good lesson for us today. We're currently living in the 19th mass extinction right now. And there's no doubt there's a press factor. There's global warming, climate change. Temperatures are climbing faster than they were dropping at the Cretaceous-Paleogene boundary. And then in terms of a pulse event, well, think of habitat destruction, pollution, hunting. All of those factors are pulse factors that are induced by us. So we are responsible for those two factors. We don't need to fear a meteorite to come and hit the Earth to cause a mass extinction, because we are right now producing both pulse and press factors that put a lot of stress on the ecosystem. So if we don't start being careful, then we're probably going to keep on pushing through that 19th mass extinction. So with this, I'd like to thank you all. I'm sorry if I went a little bit long. I'll be happy to answer any of your questions. So thank you. The authors are Arns and there you go, and West. I think it was published in Paleobiology. I can't remember the title of the paper, but yeah, it has to do something mass extinctions in the Phanerozoic or something like that. But yeah, I think it was published in Paleobiology, but I don't remember the title of the paper. Yes. You have tektites and you have microtektites, so it gives you an idea. But yeah, some of the when they're called tektites, they can be beads of maybe a centimeter in diameter. I don't know. They probably get bigger. The closer to the impact site, the bigger they're going to be. Up here in Alberta, they're called microtektites because they're really, really small. You need to look at them under a microscope because they're just looking like that at the rock. You wouldn't see them.
Isn't there a place where you found fish that have areas?
Yeah, at the Canis site in North Dakota, over there, yeah, they claim they have a site that formed right at the in response to the meteorite impact. There's fish, dinosaurs, trees that have all been pushed together, and supposedly, yeah, they would have found tektites inside the gill area of those fish. So I'm not sure how big they are, but I think they're probably microtektites.
And that they were in the gills.
Yes.
So that they.
That's another name. Yeah, tektites. It's actually spherical. Just describes the shape. Tektites is when you infer an origin, a cause for their formation.
Yeah.
So yeah, the descriptive term is spherules. That's correct. When we know that they are linked to an impact, we can call them tektites.
Okay.
Yeah. It's just like varves. Varves is basically laminations formed annually. If we know they're related to glaciers and melting ice, we call them varves. Otherwise, we call them rhythmites. It just means that they're rhythmic, but we don't infer that they are formed from a glacier.
Yeah, thank you for the presentation.
Thank you.
I'd like to ask you the diversity of the change.
Yeah.
The numbers of each species reaction.
Oh, right. This one. Sorry, what was the? They definitely looked at the species level. I'm not sure how they, because basically how they normalized it, and basically how, what were the time bins, because they had to create the time bins. Say, okay, anything from, let's say, 90 to 70 million years is all going to be in a time bin, and so on. So I'm not sure what size of time bins they used and how they normalize the data, but yeah, one curve is supposed to represent their data for, if you look at the entire world, and one is to look at the number of species at a time, time bins in North America. The issue with that is when you get to our beloved Dinosaur Provincial Park formation. That is probably one of the most fossiliferous rock formation in the world, both in terms of diversity of dinosaurs, but also sheer abundance of fossils. And that's why paleontologists before had inferred that there was a decline in diversity because as you get closer to the Cretaceous, because they went into Campanian, lots of dinosaur species because of Dinosaur Park. Other formations are less speciose because they don't preserve as well dinosaurs. But you go to a peak of all times in Dinosaur Park, and then under that, you can't compete with Dinosaur Park. All other formations will be less fossiliferous and usually preserve that lower diversity. So that's why they said, well, okay, there's a decline in diversity as you get closer to the boundary, so dinosaurs were on their decline. But that's just an artifact. If you look at within the Dinosaur Park formation, we know, I think it's, if I remember correctly, it's around 50 different species of dinosaurs from Dinosaur Park. But those 50 species did not all live together at the same time. The formation can be subdivided into a lower half and an upper half. And basically, you have half of the species living at the bottom, half of the species living at the top. So now, if your bin, you just use the entire Dinosaur Park formation to represent your bin, sure, you have 50 species living together. But if you go to a smaller time scale, then you only have 25 species living at a time. And the Horseshoe Canyon has around 25 species of dinosaurs. So basically, that's a problem. Lots of people who do run those analyses, they don't stop to think about the data that they put in the machine. Basically, they just analyze it and then say, oh yeah, look, diversity is changing. But if you really look closely, if you're aware that the Dinosaur Park formation is not all big one happy family of dinosaurs living together, all 50 species of them, then you realize that actually your diversity is different. So that's the issue with many of the analyses. They basically don't care what the data represents. They just put it in the machine, out comes an answer, and there's the answer. So, follow up? Yes?
You mentioned about the corals and the rudis. So during the, when we talk about the corals, we go back to Devonian time, and they were the the preferred reef-forming organism. And through time, they lost that distinction. Like you mentioned, in the Cretaceous, they were not the reef-forming organism. But then they returned now to being the. So was that just a series of what happened to the dinosaurs? Just different diversities of different species through time.
Can I possibly add your way on that?
Yeah, go ahead.
I think it was actually due to the different ocean types. So you have your fluctuations of like your arachnidic seas versus the calcitic seas.
Yeah, and also in the Devonian, there were different types of corals. They weren't modern corals, they were tabulate corals, for example. Now I think we have scleractinian corals, and I'm not sure if they were scleractinian corals that were extended the Cretaceous boundary. But yeah, corals have changed. Corals is just a general term to say, okay, those are colonial animals that live on branches and form reefs. But basically, they're totally different animals from the Devonian to the Cretaceous to today. So those are just replacements of corals, but we still call them corals. For the link to dinosaurs, I'm not quite sure what you mean. Yeah, yes, there were changes in diversity for sure. Yeah, because basically, that's the thing. When we talk about dinosaur species, they did not all live together at the same time. Like the dinosaurs that lived in the late Triassic are totally different from those that lived in the Jurassic. Those from the Jurassic totally different, and even within those periods, a dinosaur fauna usually lasts about 2 million years. After that, there's a faunal turnover. They're replaced by something else. So that's the thing. You have that dinosaur species go extinct, and then they're just replaced by something else. It's just that usually there's not a gap. It's just a gradual transition. Some species disappear and they're replaced by another group that takes over their place. Just at the end of the Cretaceous, there was nothing to replace them. Everything went out, and basically you had to rebuild the ecosystems from the few survivors that were left. And because all dinosaurs, except for a few lineages of birds, were extinct, and birds were already so specialized that couldn't re-evolve to be terrestrial big animals, and basically they were flying, so they had to stay in that niche. So that's why mammals were essentially the only ones that could come back and refill all the vacant ecological niches.
Thank you.
Yeah, I've actually looked for the KT in Angola, West Africa. No success due to logistic problems. I've seen it in Cuba, in Western Cuba. You can actually put your finger in contact to Western Cuba. It's a shattered carbonate. And
Yeah, they're really close to the impact sites. That's why there's very coarse blocks.
at Tanis, North Dakota, but that land is owned by ranchers.
Yes.
And it pack guns. And if you're trespassing in North Dakota, they can shoot you.
Oh, yeah.
So, you know, I've seen it in Grasslands National Park in Saskatchewan, and it's pretty good. But the best place, a nuisance farm, you know, which we take people on a field trip. And so just for the benefit of this group, that field trip will be July 5. Okay, when I'll take people there. And that nuisance, you can actually put your finger right on it, you know, like, there's Cretaceous, there's the Tertiary, there's the later, you know. But I have one question for you. So you're saying that just beneath the KPG, you can look at even down to 20,000 years, and there's some indication of, you know, variation in climate. Now, how on earth can you nail down that short a period of time? I mean, you can't do it on the basis of paleontology, so you have to do it on the basis of radiometric age dating, I guess. And is radiometric age dating now so precise that they can get those dates down to within 5 or 10,000 years? I find that hard to believe.
Yes, the way they've measured it is a lot of it is based on marine rocks that they analyze. They may have a volcanic ash that will determine the age. They won't have anything leading up, but we have the exact age for the KPG boundary because there is in Montana a volcanic ash sitting directly on top of the boundary claystone. So we have these ages there, and then they usually will calibrate. They'll calculate what was the average sedimentation rate. And then they'll basically estimate the age of their fluctuations in temperature that way. On land, it's really difficult because, as we all know, we don't have constantly sediment falling on us and basically piling up in our backyard. Sedimentation occurred during flood events, essentially. And then they'll deposit a lot of sediment, and then you'll be hundreds of years, maybe more if you're lucky, without another big flood. So there it's way more difficult. They use, again, calibration. If they have a volcanic ash and another one, they can use average sedimentation rate that they can calculate and then correct that using the maturity of paleosol. So we know that, the more mature paleosol is, the older it's going to be, and we know based on modern soils roughly how long it takes them to form. So that's usually how they try to calibrate those, but that's why we get usually big error margins. We say it's somewhere between 20,000 and 100,000 years because there's no real way to know for sure how much time that represents from that point there to the KPG boundary.
Okay. I'll try and keep it. When you were talking about everything that we know is here in North America, with our North American fossil record, but you know, there is stuff going with China. Who's going out there and saying, well, yeah, we found it here in North America, so if we're looking at the same ancient geography of Tangier or whatever. And if we go around the world, the same sort of latitude, the same sort of sea levels or moisture, we should be able to find something over here or, Angola. It's so generally, or North Australia. There's places that you're never going to find anything because nothing is ever going to be preserved in that mess. And other places that you're saying, well, if we found it like that here in North America, maybe we can find it here in Mongolia or, who's going out there to the rest of the world to try to find more information?
Well, there's people all around the world, especially the Cretaceous-Paleogene mass extinction is of such high interest.
Yeah.
People looking for that. The issue is that you need rocks that were deposited on land and that actually made it all the way to the Cretaceous-Paleogene boundary. Now, rock formation is dictated by plate tectonics. Usually you need mountains or some relief to basically shed sediment and then basically have rivers and lakes deposit them somewhere else. And then you need to have been lucky enough to have continuous sedimentation right at the boundary. So those are exceptional conditions. We're very lucky that it happened here in North America because the Rockies were there, lots of sediment was coming out. But then again, we're very limited. It only happens between Alberta and South Dakota. There's a few rocks in New Mexico and in Mexico and Texas, but it's very sporadic and you don't have continuous sedimentation. So it's really difficult to find other rocks here in North America. Elsewhere in the world, there's in Spain, what's called the Trent Basin. There are rocks that basically go all the way, basically terrestrial rocks, all the way to, I think, about 3 meters, 10 meters below the KPG boundary. But then you have a transition to marine environments. There was a transgression, and now you have deposition in the underwater in the ocean, and there you have the KPG boundary. So unfortunately, it's great. Those sections, there's one in Denmark also that spans the KPG boundary, but again, it's in marine sections. So we have lots of sites around the world in marine settings, because you need very calm environments to preserve the KPG boundary. The ash and the soot and the debris probably covered the entire planet. But if it was deposited on land, in rivers, or in trees, wind, rain probably just dispersed all that dust. The only place it was preserved is when that dust settled in a very calm environment, like in a pond, in a swamp, or in the ocean, where it could just settle down and not be disturbed by currents and just be buried under sediment that came after that. So it's very rare that you can actually preserve a KPG boundary. And most of the places around the world just don't have rocks that span that time interval. They stop a little bit before, or they just didn't form at all, because basically there was nothing, no tectonic activity happening to have rivers deposit sediment and have it preserved.
When we're looking at, say, the meteorite coming in from the northeast, and then how it would go kaboom and do what it did. So that's a science on its own. And then planet spinning, there's the high altitude winds and currents that carry things around planets. So it's never just one thing. It's looking at all of that and then looking at what the Earth was like when that happened and then how it changed.
Yeah, there's lots of different factors that have to be just right to have the sedimentation and to have preservation of that boundary. And we're just lucky that here in some places, not everywhere in North America, but in the Western interior, in some places, those conditions were there and we could preserve it. But in the vast majority of the world, one or several of those factors just weren't right, and there's no record left for that time.
Basically, just have to be a good earth sciences detective. Essentially, yes.
And so they were just going.
We actually have a couple of questions from some online participants.
Oh, okay.
Here, so
We'll come back to you.
I just want to develop this question.
Oh, okay.
How many,
Go ahead.
how many points throughout the planet will we have to estimate this kind of diversity? Right? like not just here in North America, but at other places.
So how many points is
How
that?
many areas, how many of those outcrops do we have? We can estimate the diversity in other areas.
Well, if you look at that point right here, this one, this is about, well, it's close to dinosaur park time. So for that time interval, at least in North America, there's lots and lots of rocks all along the western interior. It was a phase where the Rockies were very active and there was lots of sediment being shed towards the western interior seaway or the Verapaz Sea. So we have lots and lots of fossils for that time interval. When you get closer to the end here, the Rockies kind of slowed down. There was less of sedimentation and the western interior seaway was retreating. So the crust was rebounding a little bit. So there was not enough place to accumulate sediment. So the fossil record is poorer there. So in terms of how many exactly, I don't have the number on top of my head, but I know that, yeah, during the Campanian, during Dinosaur Park time, around that time interval, there's lots and lots of formations here and elsewhere in the world. For example, Mongolia, the rocks are the same age as Dinosaur Provincial Park. And now there's other Alaska, they're roughly the same age as Dinosaur Park, I think, or is it the same as Horseshoe Canyon, actually, so a little bit later in time. So yeah, so definitely the best record in North America is for the Campanian, and I think for the world that's also the case. But yeah, when you get closer to the end, then basically the record gets a lot poorer. And that's what, there's a study that came out this week about an analysis of the fossil record to see if dinosaurs were declining or if they were still going strong. And that's what they discovered, that the apparent pattern of a decrease in diversity is strongly influenced by the fact that we have less rock available to look for fossils at the very end of the Cretaceous than we do 75 million years ago during dinosaur park time. The environments haven't changed. They're still appropriate to preserve dinosaurs and for dinosaurs to live in, but we have a lot less rock available to us to look for fossils. So by default, just because we're searching in a much smaller area, we get lower diversity of dinosaurs, and that's what causes the illusion that dinosaur diversity is declining with time. So, online questions?
Yes, I know we're going late, so we'll maybe just limit it to one. Niels Bourdain asks, the trees were destroyed. How did they come back?
Well, there were survivors. Basically, they were wiped out here in North America, but there were refuges, some places in North America and elsewhere in the world that actually managed to do it. And we have some trees that came back from Asia or elsewhere that came back and recolonized the world. But I think, yeah, most of the trees that we have during the Paleogene, they're not Cretaceous trees. Some actually didn't make it through. And probably it's those that re-radiated, re-evolved. But there's the vast majority of trees did get wiped out and go extinct. But there were, some survivors that made it through. So new species evolved out of those. And then some were what we call immigrants that came out from elsewhere, because pollen can be transported long distances by wind in the air. So basically you have lots of new species that can be dispersed, and forests can be reestablished that way by the pollen that gets transported long distances.
But are they even able to consider, modern day zoology, biology, is you have all sorts of things transported by, like there's lots of places in Banff National Park, they won't let horses go anymore because horse poop carries live seed and they don't want oats growing in the backcountry. But that is also birds and all sorts of stuff that are carried externally and internally in little tiny animals.
Absolutely.
So, and birds.
And maybe interestingly, the only birds that survived were seed-eating birds. So maybe, they helped disperse some of those seeds back into North America. Elsewhere in the world, again, we have no idea what happened. So North America was close to ground zero, so it was the worst case scenario. But elsewhere in the world, in New Zealand, there's a KPG boundary that's deposited in the ocean, but very close to the shore. And there you see similar patterns. You see some plants survive, ferns, spikes, again, the ferns are there. But yeah, there's probably trees that survive elsewhere in the world and they just regrew from there. And even here in North America, a few did make it through, and they're the ones that actually grew after the mass extinction and repopulated the North American continent.
Well, it's our time. That's it for questions. Well, thank you all for coming today.